This video is for class 9 physics, and this is the part 2 of the numerical problems. We are studying from number 5, right? That is from exercise 4a. Okay, exercise 4a number 5. In the part 1 we are done till number 3. Number 4 was your homework, right? So let us go to number 5. Calculate the height of a water column which will exert on its base the same pressure as 70 centimeter column of mercury. So here things are given to us. Calculate the height. Okay, so of course I am supposed to use this formula, P equals to H rho G. I am supposed to calculate the height of water column which will exert on its base the same pressure as the 70 centimeter column of mercury. So two things are given, water and mercury, and they are exerting the same pressure, right? Density of mercury is also given. Okay, so now number B, will the height of a water column in part A change if its cross section of water column is made wider? If the area increases, will the height of the water column change? That's what they are asking us. Okay, let's see. Okay, let's find it out. Let's go to the solution. So coming to the solution of number 5, the things given to us, the height of the mercury column which is 70 centimeter. Here I am converting it into meter because I need to do the calculation in the SI unit. So it is 70 upon 100 meter. So next thing, the density of mercury which is 13.6 gram per centimeter cube, right, which is given to us. So taking the density of water as 1 gram per centimeter cube. Okay, so then pressure exerted by mercury should be equal to H rho G, right? H rho G. Okay, now you must be wondering why is this not converted in the SI unit, because they get cancelled, right? So therefore I am not converting them into the SI unit. So pressure exerted by mercury is H rho G, so which is 70 upon 100 meter multiplied by 13.6 gram per centimeter cube into G, where G stands for acceleration due to gravity. So again I am not replacing the values of G, right, because they get cancelled out. Now pressure exerted by water, of course I need to use the same formula because water is also a fluid. So that is P equals to H rho G, which is H into 1 gram per centimeter cube into G. I don't know the value of height of water column. This is the density of water which is supposed to know, and G stands for acceleration due to gravity. Now solving it further, according to the question, pressure exerted by water column should be equal to pressure exerted by mercury. So then I can write H into 1 gram per centimeter cube, which is the density of water, into G, that is acceleration due to gravity, should be equal to 70 upon 100 meter, right, which was the height of the mercury column, into the density of the mercury multiplied by acceleration due to gravity. Okay, now what I have done is this G here, right, this G here and this G here gets cancelled. Gram per centimeter cube and gram per centimeter cube also gets cancelled, right? Now things which is on my left hand side, that is this, I just left with H, so H comes here, equals to, right? Now solving this part, okay, I have removed one decimal, so I put a point here. I have removed one decimal. Then I have cancelled 1 0 and 1 0 here. So after calculating in all, I am getting 952 upon 100. Okay, so which is H equals to 9.52 meter. 9.52 meter. To get this SI unit directly, I have converted in the beginning. Or if you get the answer in centimeter right now, suppose, okay, if you haven't converted, then you will get the answer in centimeter, then you can convert it into meter. Okay, fine. Number B, the question was about area, right? Since P equals to H rho G, the formula does not contain area, and the pressure exerted by water column does not depend upon the area. So the height of the water column will not change. I hope you understood number 5. Now we can go to number 6. So coming to question number 6, we have the pressure of water on the ground floor is 40,000 Pascal and on the first floor is 10,000 Pascal. Find the height of the first floor. Okay, let me try to explain the question. A few things are given. Density of water, which is 1000 kilogram per meter cube, and acceleration due to gravity, which is 10 meter per second square. Okay, let me explain the question first. Okay, trying to explain question number 6. So there's a building. You can imagine a building here, right? Okay, these are the floors. So suppose a tank is kept here, a water tank. Okay, suppose a water tank is kept here, and there's a pipe which runs through the building. Okay, suppose it's a pipe. So because of this pipe and water flowing in the pipe, so the pressure exerted on the first floor, this is the first roof of the first floor, right? Okay, this is the floor of the first floor, right? And this is the ground floor here. So I am representing it by G and representing it by F. That's the first floor. So suppose the water exerts pressure here at the first floor, right? At the first floor, because of this particular height. Okay, let it be H1, right? But on the ground floor here, it will exert a pressure because of a bigger height. Let that be H2. Okay, now the question is asking us to find the height of the first floor. Let that be H. So how can I get that H? I can get the H by subtracting H1 from H2, that is H2 minus H1. I shall get the height by subtracting H2 minus H1. Now to get this height H1, what I can do is I can use the formula P equals to H rho G. Similarly here also I can use the formula P equals to H rho G, for which the pressure is given to us for each floor, right? The pressure out here is given 10,000, whereas pressure out here is given 40,000, right? So with the help of this pressure here and finding out this height here, okay, I can find the height of the first floor. I hope you understood the question. Let us go to its solution. So coming to the solution of number 6, the things given to us, the pressure at the ground floor is 40,000 because the height was more, that is H2. The pressure at the first floor is 10,000. Okay, so density of water is given 1000 kilogram per meter cube, and the acceleration due to gravity given to us is 10 meter per second square. So for ground floor, height of the water column should be H1 equals to P1 upon rho G. I hope how do you get this formula? It comes from P equals to H rho G. Okay, it comes from P equals to H rho G. Now H1 is equal to replacing the values of P, that is 40,000 Newton per meter square, rho is 1000 kilogram per meter cube, and acceleration due to gravity is 10 meter per second square. Doing the calculation and the cancellation etc., I am getting 4 meter. H1 equals to 4 meter. Out there I have used H2 to explain in the diagram. Let this be H1. Okay, I hope you understand this. Okay, now for the first floor I have used H2, whereas I have in the explanation I have used H1. For the first floor, height of the water column should be second pressure upon rho G. So H2 is equal to lower pressure, that is 10,000 upon 1000, which is the density of water, and 10 is the acceleration due to gravity. I haven't used the units here because, as you all know, after cancellation I shall get meter only because I am calculating the height. So after cancellation I am getting 1 meter. So what should be the height of the first floor? The height of the first floor should be 4 meter minus 1 meter, which is 3 meter. 4 meter minus 1 meter, which is 3 meter. The explanation part is just for your understanding, right? This is the solution which you need to do. Okay, now we can go to the next question, which is question number 7. Okay, question number 7 reads as: a simple U tube contains mercury to the same level in both of its arms. If water is poured to a height of 13.6 centimeter in one arm, how much will be the rise in mercury level in the other arm, given density of mercury is 13.6 into 10 to the power 3 kilogram per meter cube and the density of water is 10 to the power 3 kilogram per meter cube. Okay, let's try to understand the question first and then solve it. Let us try to understand the question. In the question, we are provided with a U tube here shown in the figure, and we have poured mercury in that U tube, and the level of the mercury is same on both the sides. Now what we are doing is, we are taking water column of 13.6 centimeter and we are trying to pour it on one of its arm. Okay, suppose you are pouring water whose height is now 13.6 centimeter, right? Now, as you all know, this water's height will try to give some pressure on the free level of the mercury. If it applies pressure, the pressure gets transmitted and hence this mercury level should rise a bit here. Now, to what height should the mercury level rise? That is the question, right? Now, solving it, okay, the density of water is given, which is 1000 kilogram per meter cube. The density of mercury is also given, which is actually 13,600, which is 13.6 into 10 to the power 3 kilogram per meter cube. Okay, so let us calculate the pressure exerted by the water, this red line here. Let us find this red line here. Okay, how much pressure is getting exerted on the surface of mercury with the help of this water here. Okay, so the pressure exerted by water column should be equals to H rho G. Height of the water column is 13.6 centimeter. The density is 1000 kilogram per meter cube and acceleration due to gravity I am taking as G. Now again you can ask me, I haven't converted these. This is the CGS unit here, this is the SI unit here, because they get cancelled when I am comparing the pressure. So height increased in the mercury level due to the pressure. Which pressure? The pressure exerted by the water. Again, this is also from P equals to H rho G, the same formula, right? So H equals to pressure upon density into acceleration due to gravity. Why am I using the pressure of water? Because that was the pressure exerted on the mercury column. Okay, now replacing the values, just now I have calculated it PW, that pressure exerted by the water, to be 13.6 centimeter multiplied by 1000 multiplied by 1000 kilogram per meter cube multiplied by G here. This expression here, this expression here, that is PW, right? Pressure due to water upon upon the density of the mercury, which is 13.6 into 10 to the power 3 multiplied by G. So here everything gets cancelled, right? So hence the height of the mercury column should be 1 centimeter. So because of this 13 centimeter water here, 13 centimeter of water here, okay, mercury level will rise only by 1 centimeter. 13.6 centimeter of water will rise the mercury level on the other side by only by 1 centimeter. Okay, so this much for this particular video. The other things I shall discuss in the next video. Thank you so much.